In the final years of World War II, engineers faced a terrifying problem. Fighter planes were becoming too powerful. Engines were producing so much horsepower that when pilots pushed the throttle forward, the aircraft tried to roll violently to one side. Some planes were almost uncontrollable at takeoff. Others demanded superhuman strength just to fly straight. The enemy wasn't the only threat anymore. Power itself had become the danger. So engineers made a radical decision. Instead of one propeller, they installed two, spinning in opposite directions. This was not a gimmick. It was a breakthrough that changed high-performance aviation forever. This is the story of how contra-rotating propellers saved WWII's most powerful aircraft from tearing themselves apart. In the early years of the Second World War, power meant survival. Faster fighters climbed higher. Heavier bombers carried larger payloads. Interceptors needed brutal acceleration to catch enemy aircraft before they reached their targets. Every nation, Germany, United Kingdom, United States, and Japan, poured enormous resources into squeezing more horsepower from their engines. And at first, the formula seemed simple. Bigger engine, more horsepower, greater speed. But aviation engineering rarely rewards simplicity. As engine outputs climbed past 1,500 horsepower, then 2,000, then even higher, a dangerous truth emerged. The aircraft were becoming victims of their own strength. The invisible force no pilot could ignore. Every spinning propeller obeys Newton's third law. For every action, there is an equal and opposite reaction. When a propeller spins clockwise, it doesn't just pull the airplane forward. It also twists the aircraft's fuselage in the opposite direction. That twisting force is called engine torque. In modestly powered aircraft, torque was manageable. Designers offset vertical stabilizers. Pilots applied rudder input. Training handled the rest. But World War II was not an era of modest power. As supercharged piston engines grew larger and more aggressive, torque stopped being a minor inconvenience. It became violent. At full throttle during takeoff, some high-powered fighters would lurch sharply to one side. The pilot had to fight the rudder with strength and precision just to keep the aircraft aligned with the runway. A moment of hesitation could mean veering off course, or worse, ground looping into disaster. And torque was only part of the problem. The spiral of air. Behind every propeller is a spiraling column of disturbed air known as slipstream. In single-propeller aircraft, this rotating airflow wraps around the fuselage and strikes the tail at an angle. The result? Yaw instability. The aircraft doesn't simply roll. It yaws sideways. It demands constant correction. At higher horsepower levels, this spiraling airflow intensified. The airplane no longer behaved neutrally. It wanted to twist, roll, and yaw simultaneously. Pilots described it as wrestling a living machine. And engineers understood something alarming. They had pushed the single propeller configuration near its physical limits. The power race escalates. By the mid-war period, technological escalation was relentless. Engines like the Rolls-Royce Griffin in Britain, the Daimler-Benz DB605 in Germany, and the Pratt & Whitney R2800 in the United States were producing extraordinary output. These power plants transformed fighters into monsters of acceleration. But more power required larger propeller blades to absorb and convert that energy efficiently. Larger blades created new aerodynamic challenges. Increased tip speeds approaching transonic regions. Greater gyroscopic forces during maneuvering. Heavier rotational inertia. Stronger asymmetric thrust effects. Simply making one propeller bigger was no longer an elegant solution. If blade tips approached the speed of sound, efficiency collapsed and vibration increased dramatically. Structural stresses intensified. Noise rose. Performance gains diminished. The traditional single-disc propeller was reaching an engineering wall. Something had to change. The moment of realization. Aviation engineers began asking a different question. Instead of increasing propeller diameter, what if we divided the power? What if two sets of blades could share the workload? And what if those blades rotated in opposite directions? The idea was not entirely new. Experimental engineers had explored counter-rotating systems before the war. But now the necessity was urgent. High-horsepower aircraft demanded a breakthrough. The solution was radical. Two propellers mounted on the same axis. One spinning clockwise. One spinning counterclockwise. This was the birth of the contra-rotating propeller system. Why opposite rotation matters. When one propeller spins, it produces torque in one direction. When a second propeller spins the opposite way, its torque cancels the first. The aircraft no longer tries to roll violently at full throttle. The spiraling slipstream is straightened. Yaw instability is reduced. thrust becomes more symmetrical. And critically, engine power can be absorbed more efficiently without increasing blade diameter beyond safe limits. It was an elegant mechanical counterbalance. Power met with power. Rotation answered by reverse rotation. The airplane, once fighting itself, became balanced. The engineering challenge. But elegance on paper does not mean simplicity in execution. Designing a contra-rotating propeller required an extraordinarily complex gearbox. One engine shaft had to drive two concentric propeller shafts, each spinning in opposite directions. Precision gearing. Advanced metallurgy. Lubrication systems capable of handling enormous stress. And this was wartime. Manufacturing resources were strained. Production timelines were urgent. Reliability was non-negotiable. If a contra-rotating gearbox failed in combat, the consequences would be catastrophic. So engineers worked meticulously. And gradually, operational aircraft began to adopt the system. The aircraft that needed it most. As the war progressed toward its final years, performance demands intensified further. Late war fighters and experimental high-speed interceptors required exceptional climb rates and stability at extreme power settings. One of the most notable examples was the British naval fighter, Supermarine Seafire. When fitted with the powerful Rolls-Royce Griffon engine, torque effects became pronounced. Contra-rotating propellers significantly improved handling, especially during carrier takeoffs, where deck length was unforgiving and precision was critical. In Germany, advanced projects also explored counter-rotating systems to tame immense engine outputs in prototype high-performance designs. Across the Atlantic, American engineers studied similar configurations for high-power experimental aircraft. This was not a gimmick. It was an engineering necessity born from horsepower escalation. Beyond torque, efficiency and performance. Contra-rotating propellers offered additional benefits beyond torque cancellation. Improved thrust efficiency. The second propeller recaptured energy from the swirling slipstream of the first, converting wasted rotational airflow into forward thrust. Reduced propeller diameter. Power could be absorbed without dramatically increasing blade length. Better takeoff performance. More stable acceleration meant safer runway operations. Enhanced climb rate. More efficient thrust translated into superior vertical performance. In essence, contra-rotation allowed aircraft designers to push engine development further without destabilizing the airframe. It was a mechanical negotiation between raw power and aerodynamic control, a symbol of late-war engineering. By the final years of World War II, aviation engineering had reached extraordinary sophistication. Jet propulsion was emerging. Aerodynamics were becoming increasingly scientific. Materials science advanced under wartime urgency. Contra-rotating propellers represented something profound. An acknowledgement that power alone is not progress. Power must be controlled, balanced, redirected. Without balance, strength becomes chaos. The deeper story. At first glance, two propellers spinning in opposite directions might look unusual, almost decorative. But behind that design lies a story of physics, engineering compromise, and the relentless pursuit of performance. World War II forced aviation engineers into accelerated innovation cycles. Every improvement meant survival, superiority, or strategic advantage. Contra-rotating propellers were not just about speed. They were about stability under extreme conditions. They were about transforming uncontrollable force into usable thrust. They were about mastering the invisible physics that govern flight. And as we move deeper into this story, we will explore the exact physics of torque and slipstream interaction, the mechanical design of contra-rotating gear systems, the aircraft that relied on them, and why this technology still appears in certain modern aircraft today. Because the solution forged in wartime necessity did not vanish with the war. It evolved. This was the moment engineers proved something timeless. When power threatens to overwhelm control, innovation restores balance. The physics of torque, when power fights back. To understand why contra-rotating propellers became necessary, we must first examine the physics problem that forced their invention. Every piston engine in a World War II fighter transmitted rotational energy through a crankshaft to a propeller. That propeller converted engine horsepower into thrust by accelerating air backward. But rotation does not exist in isolation. When a propeller spins clockwise, as viewed from the cockpit, Newtonian mechanics dictate that the aircraft fuselage experiences a counterclockwise reaction. This is engine torque reaction. At lower horsepower levels, say 800 to 1,200 horsepower, this was manageable. Pilots compensated with rudder input. Designers slightly offset vertical stabilizers. But by 1943 to 1945, engines were routinely exceeding 2,000 horsepower. The torque effect increased proportionally. When throttle was applied aggressively during takeoff, the aircraft rolled toward the opposite direction of propeller rotation. The left or right wing would dip violently. Rudder authority became insufficient at low airspeed. Ground loops became real threats. In carrier operations, this problem intensified. There was no room for correction on a short deck. The airplane at full power actively resisted straight flight. And torque was only the beginning. 2. P-factor and asymmetric thrust. When aircraft climb at high angles of attack, the descending blade of a propeller produces more thrust than the ascending blade. This is known as P-factor. At extreme horsepower, this asymmetry becomes pronounced. The result? Yaw instability. The aircraft's nose swings laterally during high-power climb phases. Pilots of high-performance late-war fighters often describe takeoff as the most dangerous part of flight, not combat. The more powerful the engine, the more aggressive the asymmetric effects. Engineering reality became clear. Adding power amplified instability geometrically. 3. Slipstream and spiraling airflow. Behind every spinning propeller is a corkscrew-shaped column of air. This rotating airflow wraps around the fuselage and strikes the vertical stabilizer unevenly. The tail experiences lateral force, further compounding yaw. As propeller RPM and blade diameter increased, slipstream intensity increased. In a single propeller aircraft, torque rolls the aircraft. P-factor yaws it. Slipstream twists airflow over the tail. Gyroscopic precession affects pitch during abrupt maneuvers. All forces stack together. At moderate power they are manageable. At extreme power they are destabilizing. The engineering question was no longer, how do we add horsepower? Became, how do we control it? 4. The propeller diameter limitation. Why not simply increase blade size to absorb higher horsepower? Because propeller efficiency collapses near transonic tip speeds. As blade tips approach the speed of sound, shock waves form. Drag rises sharply. Vibration increases. Structural stress escalates. Efficiency declines. This phenomenon imposed a hard aerodynamic ceiling. Engineers could not infinitely enlarge a single propeller disc. They needed another way to absorb more power without increasing diameter. The answer was elegant in theory. Divide the load between two propellers. V. The contra-rotating concept. A contra-rotating system mounts two propellers on concentric shafts. Front propeller rotates clockwise. Rear propeller rotates counterclockwise. This configuration achieves several key effects. 1. Torque cancellation. Each propeller produces equal and opposite rotational reaction. The rolling moment is neutralized. 2. Slipstream straightening. The second propeller untwists the rotating airflow of the first, converting rotational energy into additional axial thrust. 3. Improved power absorption. Two propeller discs share horsepower load, allowing smaller diameter blades while maintaining efficiency. 4. Symmetrical thrust. Yaw tendencies from P-factor are significantly reduced. It was not just a fix, it was an aerodynamic refinement. 6. Engineering the gearbox. The concept was brilliant. The execution was brutal. A contra-rotating system requires a reduction gearbox, two concentric drive shafts, precision machined planetary gearing, extreme lubrication under high stress, tolerance control within thousandths of an inch. At high RPM and high horsepower, mechanical stresses were enormous. The gearbox had to split power evenly. If synchronization failed, vibration could destroy the engine. Wartime manufacturing constraints made this difficult. But the performance benefits justified the effort. British implementation. One of the most prominent operational examples was the naval adaptation of the Spitfire lineage, Supermarine Seafire. When fitted with the powerful Rolls-Royce Griffon engine, producing over 2,000 horsepower, the torque became formidable. Carrier takeoffs amplified the problem. Short runways, flight decks, high power-to-weight ratios, crosswinds at sea, minimal correction margin. Contra-rotating propellers dramatically improved takeoff stability. Pilots reported reduced swing during acceleration, improved rudder effectiveness, more predictable handling. This was not cosmetic. It increased survivability. 8. German high-power development. Late-war German designs also explored counter-rotating systems. One example was Dornier Du 335. Though not strictly a coaxial contra-rotating system, it used push-pull configuration. It reflected the same principle, neutralizing torque effects through opposing rotation. Additionally, advanced German projects investigated true coaxial systems for extremely high-output engines, recognizing the limitations of single-disc propulsion. Germany's late-war engineering culture aggressively pursued power density. Contra-rotation aligned perfectly with that goal. 9. American high-horsepower experiments. The United States also explored contra-rotating systems in high-performance designs, including naval aircraft and late-war prototypes. A notable example: Lockheed P-38 Lightning. Though not coaxial, the P-38 used counter-rotating propellers on separate engines to eliminate torque asymmetry. This dramatically improved stability compared to single-engine fighters of similar power. The concept of rotational balance was becoming mainstream. Later experimental aircraft and post-war developments would adopt true coaxial contra-rotating systems for extremely powerful piston engines. Performance gains in numbers. Operational reports indicated measurable improvements. Reduced takeoff roll deviation. Improved climb efficiency. Enhanced acceleration stability. Reduced pilot fatigue. More predictable stall characteristics. The ability to convert slipstream swirl into usable thrust meant improved propulsive efficiency. In simple terms, less wasted energy, more forward motion. At a time when speed determined survival, efficiency mattered. 11. Combat implications. In air combat, stability at high power settings was critical. Consider a late-war fighter scrambling to intercept incoming bombers. Full throttle from runway. Rapid climb at steep angle. Tight rudder control required. With a single high-horsepower propeller, torque effects complicated this phase. With contra-rotation, throttle could be applied more aggressively. Rudder corrections were reduced. Acceleration felt smoother. Climb profile stabilized. Milliseconds mattered. Engineering precision translated directly into tactical advantage. 12. Why jets replaced the problem. By the end of World War II, jet propulsion began emerging. Jet engines eliminated propeller torque entirely. No rotating external disc meant no torque roll, no P-factor, no slipstream corkscrew. But jets introduced new challenges: fuel consumption, throttle lag, and material limits. For a brief but critical period, contra-rotating propellers represented the pinnacle of piston engine refinement. They were the final optimization of propeller-driven combat aviation. 13. Legacy beyond World War II. Contra-rotating systems did not disappear. They evolved. Modern turboprop aircraft and maritime patrol aircraft still use counter-rotating systems to manage extreme power outputs efficiently. The engineering principle remains valid. Balance rotational forces to maximize usable thrust. World War II did not invent the physics. It forced its mastery. 14. The deeper engineering philosophy. The story of contra-rotating propellers is not simply mechanical. It reflects a broader engineering truth. When a system approaches its physical limits, refinement, not brute expansion, becomes necessary. Engineers had reached the aerodynamic ceiling of single-disc propulsion. Instead of abandoning piston engines, they refined them. Instead of increasing chaos, they introduced balance. Power met with symmetry. Force met with counterforce. This was engineering maturity under pressure. 15. The end of the propeller arms race. By 1945, piston aircraft had reached astonishing performance levels. But they were nearing a plateau. Contra-rotating propellers allowed one final leap in power absorption and control. Then the jet age arrived. Propellers gradually ceded dominance in high-speed combat aviation. But the lessons remained. Balance matters. Efficiency matters. And sometimes the solution to overwhelming power is not less power. It is opposition. This was not just a mechanical device. It was a response to physics. A solution forged in war. A reminder that even the most violent force can be controlled, if understood. By the final months of World War II, the skies had changed. Aircraft were faster than anyone in 1939 could have imagined. Engines roared with twice the horsepower of early war machines. Climb rates were sharper. Acceleration was brutal. The ceiling of piston engine performance had been pushed almost to its breaking point. But what is often forgotten is this. The greatest threat to these aircraft was not always enemy fire. It was imbalance. For every increase in horsepower, there was a hidden penalty. Torque twisted fuselages. Slipstream curled violently around tails. Asymmetric thrust tried to wrench aircraft sideways during their most vulnerable moments. Takeoff, climb, and high-power maneuvering. Engineers were no longer just building faster airplanes. They were wrestling with physics itself. And physics does not negotiate. Power without control is chaos. In aviation, stability is not optional. It is survival. A fighter lifting off from a narrow carrier deck cannot afford unpredictable roll. A high-speed interceptor climbing to meet incoming bombers cannot waste seconds fighting torque-induced yaw. A naval aircraft landing on a moving ship cannot tolerate instability amplified by engine power. As horsepower increased, the margin for error shrank. Designers could not simply tell pilots to hold more rudder. They needed a structural solution. Contra-rotating propellers were that solution. Not flashy, not dramatic in appearance, but transformative in effect. Two propellers spinning in opposite directions restored equilibrium to aircraft that were becoming mechanically aggressive. It was a quiet revolution in propulsion design. Engineering against the limits. Every era of technological development reaches a ceiling. 4 piston-driven fighters of World War II, that ceiling was aerodynamic and mechanical. Propeller tips nearing transonic speed. Gearboxes under immense stress. Airframes strained by torque. Pilots pushed to physical limits. Instead of surrendering to these constraints, engineers restructured the problem. Rather than enlarging a single propeller disc, they divided the load. Rather than allowing torque to dominate handling, they neutralized it with equal and opposite rotation. Rather than accepting spiraling airflow as wasted energy, they captured and straightened it with a second stage of thrust. This was refinement under pressure. A mechanical chess move against nature. The human factor. It is easy to discuss torque in mathematical terms, Newton meters, rotational moments, aerodynamic coefficients. But in the cockpit, the problem felt visceral. Pilots gripping control sticks during high-power takeoff described the aircraft as trying to jump sideways. Some required significant physical strength to maintain alignment during acceleration. In training accidents across multiple air forces, torque-related mishandling caused crashes before combat was ever reached. Contra-rotation changed that experience. It reduced workload. It increased predictability. It gave pilots confidence at full throttle. And confidence in combat is invaluable. An aircraft that behaves consistently allows its pilot to focus on tactics rather than survival against their own engine. The bridge between eras. Contra-rotating propellers represent something historically important. They were the final evolutionary refinement of the piston propeller era before jet propulsion transformed military aviation. The late war period was a transitional moment. On one side, supercharged piston engines, complex gear reduction systems, multi-bladed propellers, aerodynamic refinement at its peak. On the other, early jet turbines, radical new airframe designs, a future no longer constrained by propeller physics. Contra-rotation was the bridge. It extracted the last increments of efficiency from propeller-driven aircraft. It allowed engineers to push power output further without destabilizing flight. It was, in many ways, the ultimate expression of piston-era ingenuity. Balance as a design principle. The deeper lesson of contra-rotating systems extends beyond World War II. It reflects a universal engineering principle. When force increases, balance becomes more critical, not less. Uncontrolled power leads to inefficiency, stress, and instability. Balanced power creates usable performance. This principle applies across disciplines. Dual-rotor marine propulsion systems. Modern turboprop transports. High-performance industrial machinery. Whenever rotational forces grow extreme, counter-rotation becomes an elegant solution. World War II engineers did not invent the physics. They demonstrated mastery over it. Why we still see contra-rotation today. Although jets dominate high-speed aviation, contra-rotating systems remain relevant. Certain modern turboprop aircraft use counter-rotating propellers to manage extremely high shaft horsepower efficiently. Maritime patrol aircraft, heavy transport platforms, and some experimental designs continue to apply the same principle discovered under wartime urgency. Why? Because the physics never changed. Torque still exists. Slipstream still rotates. Energy is still lost in swirl unless recovered. The solution forged in the 1940s remains valid. That is the mark of true engineering. The visual signature of innovation. When you look at an aircraft equipped with contra-rotating propellers, the detail may seem subtle. 2 sets of blades aligned along the same axis. But hidden inside that hub is a complex gearbox, concentric drive shafts, precision machining, metallurgical resilience, aerodynamic optimization. It is a compact monument to mechanical problem solving. And it represents an era when engineering innovation had to move as fast as the war itself. The end of the power race. By 1945, piston-engine aircraft had achieved astonishing outputs, some exceeding 3,000 horsepower. But the arms race of horsepower was ending. Jet propulsion removed propeller-induced torque entirely. The era of spinning discs pulling aircraft through the air was gradually replaced by high-velocity exhaust thrust. Yet, without contra-rotation, late-war piston aircraft would have struggled to safely handle the power levels they achieved. It was not just an upgrade. It was a necessary adaptation. Without it, the final generation of propeller-driven fighters would have been less stable, less efficient, and more dangerous to operate. A story about control. At its core, this is not simply a story about propellers. It is a story about control. World War II demanded speed. It demanded climb rate. It demanded acceleration. It demanded dominance in the vertical dimension of warfare. But speed without control is useless. Climb without stability is hazardous. Power without balance is destructive. Contra-rotating propellers transformed overwhelming engine output into disciplined thrust. They allowed aircraft to harness strength without surrendering stability. And that transformation is what defines true innovation. The quiet legacy of a wartime solution. History often celebrates the dramatic, the dogfights, the bombing campaigns, the jet breakthroughs. Less often do we pause to consider the engineering refinements that made those events possible. Contra-rotation is one of those refinements. It does not roar like a jet engine. It does not dominate headlines. But it solved a fundamental aerodynamic crisis at the peak of piston-era aviation. It allowed engineers to push boundaries without losing control of their machines. It represents the moment when brute force gave way to balanced design. Final reflection. When you watch a World War II aircraft equipped with contra-rotating propellers, you are witnessing more than an unusual mechanical arrangement. You are seeing Newton's laws countered with precision, torque answered with symmetry, instability corrected with engineering discipline. You are seeing balance imposed on chaos. And perhaps that is the deeper message hidden within this wartime innovation. Progress is not just about increasing power. It is about mastering it. As aviation moved into the jet age, the double-spinning propellers of World War II gradually faded from frontline service. But the lesson remained embedded in aerospace engineering forever. When power threatens to overwhelm design, add balance. When forces spiral out of control, counter them with equal force. That is how engineers solved power and torque in high-horsepower World War II aircraft. And that is why contra-rotating propellers remain one of the most elegant solutions ever devised in the history of flight.